Hello everyone. In the last class we have discussed probability of error calculation for QAM constellation and also for orthogonal signal sets like FSK, PPM, etc. In this class we will continue our discussion on probability of error calculation and see how to compute probability of error for biorthogonal signal set, and then we will also see how to compute an upper bound on probability of error for some signal set for which computing the exact probability of error is not so simple, like orthogonal and biorthogonal signal sets. For orthogonal signal sets, we have already seen that the expression is too complicated to be computed in closed form. So, for that kind of signal sets, only way to compute the probability of error is by numerical integration, and for such signal sets often we can compute a reasonably good upper bound on the probability of error. So, that will give us also some idea about how good the signal set is. So, let us see how to compute the probability of error for biorthogonal signal set first. So, here for a biorthogonal signal set we have some n number of signal points of this type, and then this has, so we know that the dimension is n and number of points is 2 times n. So, there are n number of components, and the ith signal point for I equal to 1 to capital N is this, and then the whole signal set is S1, S2 to Sn, then the negative of them minus S1, minus S2 till minus Sn. Okay. And how do we detect? We know that the ML detection can be done by seeing the distance of the received vector from all the points. But when we try to look at the condition carefully for a biorthogonal signal set, we will see that a simple rule comes out from that condition, and that is, we simply take the received vector R, which has n components R1, R2, Rn, then see which of these components has maximum absolute value. That is, if it is negative, we take the negative of that to make it positive. We make all the components positive and then take that component which is the maximum, and then if that component is positive, then we take, suppose Ri is maximum, the absolute value of Ri is maximum, then if Ri is positive we take Si, we detect Si, if Ri is negative we take minus Si. So, that is the simple detection rule, and that is the ML detection rule. So, what is the detection rule? We can say that the detection rule is that choose Si if, so Si will be chosen if, so remember that Si has all the components zeros and only the ith component 1. So, Si will be chosen if Ri, the ith component, is greater than 0. If it is not greater than 0, obviously the point is nearer to minus Si than Si. So, there is no reason to choose Si at all. because minus Si itself is a better signal point nearer to the received vector. So, Ri has to be greater than 0. So, if Ri is now greater than 0, also the other components of the received vector should be less than this value, because otherwise some other signal point is nearer to the received vector. So, that means Ri is greater than Rj for all j not equal to I, and also it should be greater than the negative of Rj, that is, there should not be any other component whose absolute value is greater than Ri, even though that value is negative and it is less, as a result it is less than Ri, but its absolute value itself should not be greater than Ri. Then if it is so, then if it is not, if the value is negative and its absolute value is greater than Ri, then minus of that corresponding signal is a better choice. So, Ri should be greater than minus Rj also for all j not equal to I. Similarly, we should choose minus Si as the signal point if Ri is less than 0, and then minus Ri, remember Ri is less than 0. So, minus Ri is positive and it should be greater than Rj, and minus Ri should be greater than minus Rj also. So, these two conditions together here actually means that Ri is greater than the absolute value of Rj, these two together means, and here it means that minus Ri is greater than absolute value of Rj. So, this is for all j not equal to I, this is for all j not equal to I. So, this is the detection criteria. Now, like the orthogonal case, this biorthogonal signal set is also a symmetric signal set. So, as a result, the probability of error for all the signal points will be same. So, it is sufficient to compute the probability of error assuming that one of them is transmitted. That is, just compute the probability of error for one of the signal points, and that is going to be the probability of error for all the signal points, and as a result that is going to be the average probability of error of the signal set. So, we will compute the probability of error for one signal point, that is S1. So, we will assume that S1 is transmitted and try to compute the probability of error. That will be the average probability of error. So, we want to compute the probability of, we assume that S1 is transmitted and we also know that the correct decision is made, correct detection is made if R1 is greater than 0, because for S1 to be chosen at the detector, R1 has to be greater than 0, and also R1 has to be greater than mod Ri for all I not equal to 1. So, what is the probability of correct detection if S1 is transmitted and we know that R1, so R1 is greater than this and R1 is greater than mod Ri for all I not equal to 1, and let us take the value of R1 to be alpha, just like orthogonal signal set, the way we computed, we assume that R1 is equal to alpha and alpha is greater than 0, because R1 needs to be greater, if R1 is alpha is not greater than 0, then there is a error. So, suppose we know that R1 is equal to alpha and alpha is greater than 0, then what is the probability of correct detection? Probability of correct detection is the probability that all the other Ri's absolute values are less than R1. So, all the components Ri's where I is not equal to 1 are nothing but the noise values in those components, noise components, and those noise components are independent of each other. So, the probability of their being less than R1 factorizes into individual probabilities, because the noise components are independent. So, this becomes the probability of a noise component being so that the absolute value is less than R1, that is the noise component being in the range minus R1 to R1, that is minus alpha to alpha. So, that probability is obtained by integrating the density function of the noise component in the range minus alpha to alpha, and then there are n minus 1 such value of I not equal to 1. So, excluding 1 there are n minus 1 other dimensions. So, n minus 1 is power. So, probability of correct detection is known to be probability of correct detection given that S1 is transmitted. Now, this is obtained by averaging this over all values of alpha above 0. So, we have to integrate this from 0 to infinity, alpha varying from 0 to infinity, and then we have to multiply this by the density of R1 at alpha, and then integrate that. So, now R1 is nothing but the first component that was transmitted is root over Es. So, root over Es plus N1. So, if R1 is alpha, that means that N1 must be alpha minus root over Es. So, the density of N1 is known. So, we have to take that, evaluate the density at this point. For R1 to be alpha, N1 must be this value. So, Pn alpha minus root over Es, and then take this minus alpha to alpha Pn x dx n minus 1 d alpha. Now, here this n is m by 2. So, we can, if we want to write it in terms of m, then we have to write this as m by 2. So, here also the probability of correct detection is written as an integration, and this is not so easy to compute. So, but this can be computed numerically, and there is no other simple way of computing this. So, both for orthogonal and biorthogonal signal set, the form of the expression, the probability of error that we have computed is similar, and they can be computed numerically. But can we get a reasonably good estimate of the probability of error? This is the exact probability of error, but can we get a reasonably good estimate of the probability of error in a simpler manner? That is the question. So, the answer is yes, we can get an upper bound of the probability of error by using what is known as the union bound. Remember that we discussed, when we discussed the background on probability, that there is something called union bound on the probability. That is, if there are some events E1, E2 till E say t, then the probability of the union of the events I equal to 1 to t ei is less than equal to the sum of the individual probabilities of the events. This is the union bound. So, we will use this to get an upper bound on the probability of error. So, suppose that, so this we are discussing union bound on probability of error. And now suppose S1, S2 till Sm is the signal set. And S1 is transmitted. Now, for I not equal to 1, we define the following event. Define the event EI to be the event that the received vector R is nearer to Si than S1. So, I is not equal to 1, and if Si, the ith signal point, is nearer to the received vector than S1, we say that E1 has happened. So, EI is that event. Now, what is the probability of correct decision? Probability of error given that S1 is transmitted. We know that if S1 is transmitted, there will be an error in detection if we detect something other than S1. So, that means that one of the other signal points is nearer to the received vector than S1. So, that means one of the events E2 to EM has happened, only then the error can happen. So, if there is an error in detection if S1 is transmitted, then that means that one of the other signal points is nearer to S1. That means one of the events just now defined is correct, true. So, that means this probability is nothing but the probability of the union of these events, I equal to 2 to m EI, and from the union bound on probability, this is less than or equal to the summation I equal to 2 to m probability EI. So, and often this is easier to compute. Probability of individual EI is often easier to compute, and we will see for some particular examples for which the exact probability of error calculation was not easy, that this becomes easy to compute. So, let us take those two examples, orthogonal signal set and bi-orthogonal signal set. So, orthogonal for orthogonal signal set, the probability of error is same as the probability of error given S1 is transmitted. So, we need to compute this. Now, the event EI in this case is the event that the received vector is nearer to Si than S1. Now, the distance between S1 and Si is same for all i's, not equal to 1. So, and that distance is root 2 times root over Es. Root over Es times root 2. So, we know the distance between 2 points, and what is the probability that the received vector 1 is transmitted, what is the probability that the received vector is nearer to the other point than the transmitted point. That we know, that is the probability of error for PAM. We have computed that. So, that probability is known. So, this is by union bound, this is less than equal to summation I equal to 2 to m probability of EI, and this is summation I equal to 2 to m, and probability of EI is q of d by 2 by root over n naught by 2. And what is d by 2? It is, the d is root over 2 ES, and that by 2 means, so root over 2 ES by 2 by root over n naught by 2. So, we get this is, and this does not depend on I. So, this is basically m minus 1 times, there are m minus 1 copies of this being added. So, this times q of root over ES by n naught. So, this is a this is an upper bound of the probability of error for orthogonal signal set, and this is the union bound on the probability of error, and this is quite simple compared to the exact probability of error, and this only needs the value of q at some point. Okay. For biorthogonal signal set, probability of error again is, because the signal set is symmetric, we have probability of error given S1, and now the events here are slightly different. There are m points, m is equal to 2n, and out of, so if we take S1, there are S2 to Sn and minus S2 to minus Sn, there are these 2 times n minus 1 points. 2 times n minus 1 points are there which are along other dimensions, but there is one point which is in the opposite, which is the minus S1. So, the distance of minus S1 from S1 is different from the distance of the other signal points from S1. So, what is the distance of the other signal points from S1 is the same as what was here, root 2 ES, but what is the distance of S1 from minus S1? It is 2 times root over ES. So, those two distances are different. So, just consider the case of 2 dimension, that is n equal to 2, m equal to 4. So, we have this. So, this becomes the 4PSK signal set actually like this. So, this is S1, this is S2, this is minus S1, this is minus S2. So, the event this is transmitted, this distance is different, this distance is same as this distance, but this distance is different. So, all the points have same distance from S1 except for minus S1, that has a different distance. So, that will be computed separately. So, consider all the other points, 2 times n minus 1 such points, for them the probability of that event of being detected as is q of this root over ES by n naught, and there are 2 times n minus 1 such points, and there is one more point. So, remember this summation is there and we have taken so many terms, so many events, one more event is left and that we have to add. So, that is q of that distance is 2 times root over es. So, we will have here 2 es by n naught. This is the union bound on the probability of error for bi-orthogonal signal set. And this is also quite simple. It is only expressed in terms of the q that needs to be evaluated at 2 different values. So, we have so far seen how to compute the probability of error exactly for QAM constellations, PAM constellation, and for any binary signal set, and we have seen that all those probability of errors can be computed or expressed in terms of the Q function in a simple manner, but for orthogonal and bi-orthogonal signal set the probability of error cannot be expressed in such a simple way in terms of Q function. There is integration involved and those integrations need to be done numerically because the inside integrand is not a closed form expression, it has Q function inside it. So, though those functions, those probability of errors can be computed numerically, often we need some gross idea about the probability of error which need not be very accurate. So, for that this union bound on the probability of error will serve the purpose. So, now for a better understanding of, to get a good feel of these calculations and also to develop confidence in these formulas, one needs to verify that these formulas actually give you the probability of error and their bounds quite correctly. So, for that one can do Matlab simulations. It is very helpful if you do Matlab simulation on take a signal set, take FSK signal set or take a QAM signal set and transmit from the signal set randomly with uniform distribution on all the points, transmit the points say 1 lakh points and find out the probability of error. At the receiver you do the detection by ML detection according to the rules that I have just now said, and for QAM you can simply take based on the Euclidean distance or try to simplify it. Along each dimension you can do independently if it is 16 QAM or any rectangular QAM constellation, and then you get a probability of error, average probability of error from the simulation. So, that is error rate. That need not be exactly same as the probability of error, but there will be slight variation. And then you can compute these probability of errors from the formulas we have just now developed. Again for computing you can use Matlab function ERFC to compute the Q function values, and then also to compute the integrations involved you can do numerical integration either in C or Matlab. Better to in Matlab because you have ready made function for Q at least, and then you can compare the exact probability of error that you have computed, the union bound that you have computed, and the error rate that you have found using simulation. These 3 things can be compared, and all these 3 quantities can be plotted against the average signal energy or even SNR, ES root over ES by n naught. You can vary ES by n naught and plot these 3 quantities. Do the simulation again and again for different ES by n naught. Keep the n naught fixed and change the ES, or keep ES fixed and change n naught to get different ES by n naught, and then compute and simulate all these values and plot them in a single figure. and then find out how they compare. That will give you some good idea about how good the union bound is, for example, and also the fact that simulation gives you a value, probability of error value near enough to the computed value will give you some confidence about these formulas. Okay. So, this is all about probability of error calculation that we wanted to discuss in this course, and now we will move on to the next topic, that is the modulation with memory. So far we have discussed modulation techniques without memory. In each symbol, what we transmit depends only on the information bits that we wanted to transmit. It did not depend on what we transmitted before. So, what we will discuss now, the modulation techniques that we will discuss now, there we will see that what waveform we transmit now will depend on not only the information bits that we transmit now, but also on what waveforms we transmitted before. So, that means the modulator has some memory in it. Its transmitted waveform depends on what it transmitted before, not only on the input information bits, but also on what it transmitted before. So, that is why the modulator is called, this technique is called modulation with memory, because the modulation remembers what it transmitted. So, it has some memory. So, we are considering modulation with memory. We will just discuss some simple examples of modulation with memory. First of all, we will consider some baseband modulation. So, we want to transmit 0, 1. Traditionally, we either we assign two levels for 1 and 0, and then transmit those voltage levels. And either it may be plus 5 volt and 0 volt. For 1 it is plus 5 volt, 0 for 0 volt, or but then there the signal value is returning to 0 whenever the bit is 0. So, that is returned to 0 whenever there is a 0 bit that is to be transmitted. But there is another scheme where the transmission of 0 is not preferred, but you transmit the negative voltage for 0. That is called non-return to 0 scheme, because you do not return to the 0 voltage, but go to the negative voltage, toggle between plus and minus voltage. So, that is called non-return to 0, or abbreviated as NRZ. So, there let us say you want to transmit 1 0 1 1, then 0 0 0 1 and so on. Then here we will transmit for 1 a high voltage, then a low voltage, then 1, another 1, then 0 0 0, then 1. So, this voltage will be say A, and this will be minus A, the negative voltage. The 0 voltage is some in between. Now, this does not have memory, because what voltage level is transmitted here does not depend on what was transmitted before. So, this is not a modulation with memory, but this following scheme is a modulation with memory, NR, this is called NRZI. Here the voltage level is changed from the previous level if a 1 is to be transmitted. So, for example, here initially we transmit minus A voltage, then a 1 is to be transmitted. So, we change the voltage to plus A, then we transmit this level, but then 0 is to be transmitted. So, we do not change the voltage. So, whether the voltage level will be changed to the other level or not depends on what we want to transmit. So, 0 means no change of voltage level, then again 1 means change of voltage level, then again 1 means change of voltage level, then zeros, 0, again 0, then 1. To transmit 1, we will change the voltage level. So, this is A and this is minus A. So, this scheme now has some memory, because what we are transmitting here depends on what we transmitted before. For the same bit 0, here we transmit 1, here we transmit 1, 1, 1, but at some other time we will be transmitting 0. For example, if a 0 came after this, we will not change the level and we will keep transmitting 0. So, for the same bit 0, sometimes we transmit 1, sometimes we transmit 0. So, it does not only depend on what we want to transmit, but it also depends on what we transmitted before. So, if 0 is to be transmitted, we keep the previous voltage level in this time slot also. So, that means we have to remember the previous voltage level. So, this has some memory. This encoding can be also expressed in this fashion, that the present voltage level, let us call it Bk. Suppose this is, if we assume it to be 1 0 instead of plus A and minus A, just assume this level to be 1, this level 0, then the present bit is, the transmitted bit is the AK. AK is the information bit, kth information bit. What is the input? And then XOR it with the previous level, previous bit that we transmitted, that is Bk minus 1. This is called differential encoding. So, here this is how it is. So, for example, take this, we here Bk minus, so we want to find out what we need to transmit here. So, the encoder will decide what is to be transmitted here. So, it needs to transmit 0. So, that is Ak is 0, and then Bk minus 1, what was transmitted before, is 1. Here this level is 1, it is not this bit, but it is this level, that is 1, and this level is 0. So, Bk minus 1 is 1 and 0 is to be transmitted. So, 1 XOR 0, that is 1. So, it transmits 1. Then for this Ak is 1 and then this level is also 1. So, XOR it, you get 0. So, you transmit 0. Then this is Bk minus 1 is 0 for the previous, for this, and this is 1. So, 1 and 0 you get 1. So, you get this. This is differential encoding, and from this one can see that the decoding must be, can be done in a simple way as Ak is Bk minus 1 XOR Bk. So, you just take the two consecutive symbols, two consecutive time slots, XOR the levels you have got, and that will be the information bit. Take this XOR this will be this bit. So, these two are same levels, so XOR will be 0, 0. These two are different levels, the XOR will be 1, so 1. These two are different, so 1. These two are same, 0, and so on. So, the decoding is very simple. And this encoding is expressed in terms of a state diagram, very simple manner. Say the encoder has two states, S0, S1. So, S0 denotes what was transmitted, the 0 level that was transmitted, and S1 denotes the 1 level. So, the encoder is at 0 level, means it is in S0 level state. If it is here 1 level, it is S1 state. So, if the signal, this level signal A, voltage level A is called, suppose we say that that is ST, that is this pulse, the value 1, and the negative is minus st. So, if it is encoder is at state S naught, that is it is 0, then if it receives 0, then it will be there in that state. It will transmit the same minus st level. This is minus st. So, if it receives 0, what will be transmitted is, so it receives 0, then it will go to S naught itself, because the next level it is going to transmit the same minus st waveform, and so minus st will be transmitted and it will go to the same state. It will remain in the negative state. If it receives, if it wants to transmit 1, then it will transmit st, that is the positive level, but then it will go to the next state, because for the next time slot it will be in the higher state. So, the state is changing, it is coming to S1 state. Similarly, if it is in the higher state, if it receives 0, the state will not change and it will transmit st. If it receives 1, it will change the state and it will transmit minus st. So, this is the state transition diagram of the encoder. Now, similar to this scheme is, there is a passband modulation scheme called Differential Psk, or abbreviated as Dpsk. Now, let us take an example of Dqpsk, where Qpsk constellation is used, but differential encoding along with Qpsk constellation. So, we have Qpsk constellation, and traditionally what we do is we encode the 2 bits into one of these points and transmit. So, that means the actual phase of the signal that we will transmit depends on what bits we want to transmit. If we want to transmit, say m equal to 0, we will transmit this point, this is S1, this is S2, this is S3. So, m equal to 0, 1, 2, 3. For this, we will transmit corresponding point. But in Dqpsk, just like NRZI, we do not transmit the exact point based on what we want to transmit, but we change the phase based on what bits we need to transmit. If we want to transmit m equal to 0, we do not change the phase. Whatever we transmitted in the last symbol interval, we transmit that. Now, if we want to transmit 1, we rotate the point. Whatever we transmitted before, whichever point we transmitted before, we rotate the point and take the next point in the anti-clockwise direction and transmit that point. If you want to transmit 2, we rotate it by 180 degree 2 times and then transmit that point, and so on. So, again here, just like in NRZI, what we transmit now depends on what we transmitted before as well as what information we want to transmit. That is, the phase difference between the previous symbol and the new symbol has the information. The information is contained not in the phase of the absolute phase of the present waveform, but in the phase difference between the previous waveform and the present waveform. So, the information is encoded in the phase difference between the 2 consecutive symbol intervals. So, the phi k, the kth phase of the signal that will be transmitted is phi k minus 1 plus the kth m, that is the kth symbol that will be that needs to be transmitted, times pi by 4. This is pi by 2. So, if mk is 0, then you transmit phi k minus 1 phase itself. If mk is 1, then you transmit phi k minus 1 plus pi by 2. That is, if previously you transmitted S1 and now you want to transmit 1, you transmit S2. Rotate it once and transmit S2. Okay. So, now how do we demodulate? Of course, we can do exactly the same way as in at Zi, and we first find out what is the phase of the received signal, that is we find phi k, and then previously we actually found phi k minus 1. So for every k you find phi k, and then mk is determined by phi k minus phi k minus 1. Take the phase difference between the present and previous symbols, and that times 2 by pi is the symbol that was transmitted. Okay, but here we need to find phi k, but phi k may not be, it may be sometimes difficult to get exactly, because often what happens is that carrier phase is shifted when it goes through the channel or some part of the receiver. So it is often difficult to estimate what exact phase the carrier has, the transmitted signal had at the receiver. So in such situations, when it is difficult to compute phi k, or when the carrier phase is shifted by some constant, and as a result it is difficult to get the absolute phase of the signal, so we do not want to compute this. But can we get this difference without computing this itself? So of course there is a constant shift that will cancel when you subtract these two, but even without computing this, we can get this directly from the received signal in the following way. So that is the method 2. So method 2 is this: we take received signal, and from an oscillator we generate cos omega c t and sin omega c t multiply pass through matched filter and then sampler then here we actually get the real part of the received vector, that is over Es cos phi k minus possibly some constant phase shift that we were talking about, and plus some noise nk1. This is after doing the correlation with the pulse actually. So this is the real part of the received vector, two-dimensional vector, and then we also get here the imaginary part Es sin phi k minus theta plus n k2, and then we also delay it, that is we want the previous received vector. So we delay both these, pass through a delay, and then this comes here after delay, and then so we have the present received vector here and the previous received vector here, and we compare the phase between these two vectors. So we can compute the phase difference and decide on the phi k minus 1, and mathematically it means that we are computing r k, the received vector, that is root over Es cos phi k minus theta plus j times root over Es sin phi k minus theta, this plus noise, this plus noise, and then we have passed it through delay. So, we have got Rk minus 1 also, and then we take Rk. What phase comparator does is it can simply multiply this, take the conjugate of Rk minus 1 and multiply with Rk. That will give us, see that this signal part, if you neglect the noise part, this is basically e to the power root over es times e to the power j times this. So, you get Es, when you multiply these two, you get Es e to the power j phi k minus theta minus phi k minus 1 plus theta, that is we get phi k minus 1 and plus some noise term. So, if you now take the phase of this Rk minus 1, the phase of this will be this phi k minus 1 and plus some noise component will be there. So, this part has the information. From here we can find the information. If it is pi by 4, the bit is, if it is 0, bit is 0, symbol is 0. If it is pi by 2, the symbol is 1. If it is pi, symbol is 2, and so on. So, there will be some deflection due to noise, but we will get the approximate value. So, this is how one can decode the Dqpsk, detect the Dqpsk signal without explicitly computing the exact phase of the signal. So, both Dqpsk and NRZ, these are all modulations with memory. One is baseband, the other is passband, and there are other schemes which we have not discussed. These are just the basic schemes. Well, that's all. Thank you.